All right, to wake all of you up, I have some jokes for you. Yeah. Days ago, I watched some kind of TV program about the female in the industry, especially for cooking. And one of the lady from Hong Kong, she said that when she started in Hong Kong from her childhood, actually we are the typical Chinese student, right? And it means under the influence of Confucius, actually we only listen to the teacher and we don't respond to anything. We don't ask question. We are really, really silent. But when she went to USA to pursue her degree for cooking, anyway, she was amazed. In the class, the students ask any kind of silly question. Never mind. The question is make sense or not. The student only they simply ask. They don't think in advance. They simply ask. But never mind what silly question the student raised. The professors always listen to the student and say, in some way it makes sense. Yeah, they don't criticize. Oh, no, that is really silly. No. Sorry for that. Yeah, that is the big difference. So the lady was inspired a lot. Don't be silent. You can ask any kind of question. You can answer any kind of silly question as you like. Yeah, through such kind of process, your thinking will be activated. Okay, so don't be shy. Yeah, the lady right now become very famous for cooking in Hong Kong. Yeah, and also that we have some simple equations. For example, you learn something from myself, right? And how much you capture it. Did you get the point? That is the question. Okay, so you can see if for everything I teach you, some kind of very small issues, just like the function of differential pair, blah, 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 many of them, right? Don't think, oh, they are so small. Okay, yeah, they are really small, right? But if you sum all of them up, okay, well, it means what? Even for such kind of small terms, if the number is huge, then it will approach infinity, right? That is what you can enhance your design capability to get much better future for your own lives. And according to teaching and learning, what I teach you, if you only learn 99%, you say, oh, 99%, only 1% less. Oh, sorry for that. Yeah, after such kind of knowledge passing, and again, right? If the number is increased, what is the consequence? It will approach zero. So hopefully, you learn something from myself and then enhance it. Okay, even a little bit better than myself, then you will get this one. If the number is increased, then it will approach infinity. Never mind how much improvement, enhancement you get from myself. Your future, I promise you, will be much better than mine. Okay? So, not only keep listening, but understanding. To get better understanding, 1% better in understanding means infinity for your own future. 1 less percent in understanding means almost nothing for your future. Okay? It will make a huge difference even with 1% more or less. So just encourage yourself to get better understanding than your professors and your mentors, then your future won't be limited. Okay, it will become unlimited. That is what I hope all you guys can get. All right, let's go further. For such kind of innovation, how can we survive for op-amp design, I mean to provide high enough gain under low supply voltage. That is the major challenge for new processes we need to face. Okay? Yeah, anyway, we have advanced op-amp design, we have emergent, especially for this one. Yeah, okay, maybe moments later, we will touch this for low supply voltage design. Okay, and yeah, anyway, I think how can I say, the order of the slides needs to be changed because we mentioned it already. One, that is quarter, counterpart, then left half, right half in the middle. Okay, yeah. Anyway, it is created more than 30 years ago. Yeah, and again, boosted. Okay, folded, folded. Yeah, folded. If you remove it, then flip it up, it will look exactly the same, like this. Okay, yeah, that is what I can help. If you are not happy, you would like to increase the gain even further, then you can combine most of them, not only cascade, but also cascade. This is for cascade, and this plus that for cascading, right? But this is only 1/4. So again, 1/4, right? Then, sorry, yeah. You have quarter, then counterpart, then left half, right half in the middle. Allow me to show you the final result. Look like this. Okay? Yeah. And it is created about 2 decades ago, 20 years ago. All right? Anyway, nothing is new. Nothing is new. If you go to the bottom, see, it is published in such kind of top 1 IC design conference. It is even harder to get paper accepted for top 1 IC design conference than top 1 IC design journal. My lab published 2 top 1, oh, sorry, the SSC. Yeah, and top 2, TKS1, blah, 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 but till now, 0 for top 1 IC design journal because it is really tough. Okay, some kind of mission impossible. Yeah, anyway, hopefully in the future, some professors, students in this university can publish something on this. All right, till now, not only 0 for my lab, for all the professors. Okay, it's too tough. But nothing is impossible. Hopefully in the future, or even in the near future, somebody will do something to enhance our our image around the globe for IC design. Okay, then go for the final one, emerging. Yeah, design strategies. Anyway, for open loop amplifier, if it is open loop, just like a comparator, right? Yeah, it is highly process dependent. Then for most of the existing amplifier, their linearity and accuracy actually are not good enough. All right. And for feedback, it means closed loop. This is open loop, that is closed loop. Yeah. For closed loop amplifier, we have feedback network. So it means that you need to have good matching for passive component. I mean for feedback circuit. It is not any kind of mission impossible. Yeah. For resistor, usually for the feedback or capacitor, usually not. Usually with resistor, right? Can we match them? Piece of cake with good layout, then you can make it. Yeah. Anyway, anyhow, the only problem is we need to have high enough gain to be sacrificed for closed loop, especially for negative feedback closed loop application. Okay, so that is the most difficulties you need to face for new processes. Okay, for open loop, linearity and accuracy actually really bad. Okay, and for feedback, you don't need to pay attention to matching. for resistors especially. However, under very low supply voltages, how can you provide high enough gain? Yeah, maybe you say, hey, we try to improve the linearity, the accuracy for open loop application, and we can enlarge the gain for our op-amp. Yeah, we have many kind of, even moments ago I showed you, wow. You can combine all the techniques you learned from your professors, from the papers, books, anyway, anyhow. You can see if you lower the VDD, then sorry for cascode. It becomes some mission impossible to survive under very low supply voltage, right? Yeah, that is really upset. So that is what we hope for open loop, for closed loop. However, you can see, yeah, for new processes, it becomes even more nonlinear than before. And that is for open loop, right? And how about closed loop? Again, the supply voltage becomes lower, cascoding becomes mission impossible. It is really hard to enhance the gain. Okay, so till now, no major breakthroughs for low voltage design. That's it. That is the ugly truth. Okay, it means what? For open loop, if you would like to improve the linearity and the accuracy, you can see very few success, and never mention about the gain under low voltage design. It means we need new ideas. We need innovation, okay, for such kind of low voltage processes. Then let's go back to check what we have, what kind of weapons we have to deal with such kind of low voltage processes. I mean, for gain. Cascading? It is impossible. Even though for each stage the gain is reduced, right? But we can enhance the gain by cascading more stages. Piece of cake. However, I told you already, for closed loop operation, at most only 2, no more than that. All right? For open loop operation, this is still possible. For example, for your comparator design, even under low voltage processes, you can still make something out of nothing. But for closed loop applications, that is the most. Okay, sorry for that, only 2. And for each stage, according to low voltage, it means the gain will also be reduced. So you have only A1 by A2, never by A3, right? It is reduced, Sorry for that. The gain will far less than enough. How about cascoding? No, because the voltage is too small. Okay. How about cascoding? If you have this term, cascading, forget about it. No. Okay. So only this one may be possible. We have the so-called negative impedance compensation. Okay, the key word is negative impedance. And what is that? Later I will show you. Another very important small circuit for your own future. It is good for low voltages. It can provide very high gain. However, I need to warn you, the linearity is really bad. Okay, luckily enough, usually we only require high enough gain for op-amp. We pay not much attention to the linearity. We only pay attention to the linearity of what? Of the closed loop application. Instead of the op-amp inside the closed loop. No. Okay? And through the closed loop operation, especially through negative feedback of the closed loop, we can enhance everything by sacrifice the gain. So the key issue is still to design high enough gain for the op-amp, even under low voltage processes, and then we can sacrifice the high enough gain, yeah, to enhance all the others, including linearity, including accuracy. Yeah. But before that, I would like to wash your brains again. Okay? Because from microelectronics all the way to analog IC design textbooks, almost everybody tell you to design stable op-amp. In the past, it is good. But nowadays, if you would like to design something for 5 nanometers, 7 nanometers, or even 28 nanometers, the supply voltage is too low. Okay? The gain won't be good enough. If you would like to take care of the gain and also the low supply voltage, it is almost impossible. Okay, so let's go back. Let's go to the bottom to ask ourselves what kind of stability is really required for our IC design. Okay? So from the very beginning, yeah, do you need a stable op-amp? Or you only need stable op-amp application? I mean, after you put the op-amp into the closed loop application. All right? Yeah. In theory, no. Okay, I only mentioned in theory, not in practice. No. Right? Only if, because we only focus on the final circuit. I mean, on the closed loop application. Only if the application is stable. It should be. If the closed loop application, that is the final product. If the final product is unstable, then everything will go wrong, right? So in theory, we only focus on this instead of that. Okay? Yeah. So, in practice, I would like to ask you, does a stable op-amp application require a stable op-amp? In the past, everybody told you to design a stable op-amp for a stable op-amp application. That is always. That is the always case instead of usual case. Okay, but in theory, no. However, I will pretend the question is open here. We have no idea whether or not. Allow me to show you some examples, maybe only 2. Okay. This is some kind of bridge T by quad filter structure. Humankind used it in 1970s. Okay, wow, 50 years ago. Your grandparents learned it already. Okay, and this is some kind of op-amp, and this is the filter structure, blah, blah. Yeah, that is only a black box. If you go to the bottom, to see a very popular in 1970s. Okay, if you go to the bottom to see the detail of the circuit, it looks like this. If you forget about the others, only look at this. I think most of you will be scared. Why? Why? Because the input from here, the output is fed back to the positive terminal, right? It means what? With such kind of positive feedback, usually this circuit will become unstable. But in 1970s, That is the overall circuit look like this. It is stable. However, this one is unstable. Sorry for that. If you calculate, how to calculate? We have only some kind of rough estimation with dominating power approximation or single power approximation. Yeah, we have only P1. And all the other poles or zeros, they are simply too far away, out of the interest band. Out of the band we are interested. Okay, then forget all of them. That is the so-called dominating power or single power approximation. So the both plot look like this, and forget about the others because they are far away. Okay. Yeah. If you calculate, then you will know this structure will have right half plane power. It is totally unstable. But you put this kind of unstable amplifier into such kind of negative feedback, the application is stable again. Otherwise, humankind in 70s, they will not use it, right? It is quite stable. Then humankind would like to use it, and if you only look at the amplifier itself, it's really unstable. Okay. Yeah. Anyway. Yeah. Okay. This is unstable for some kind of very simple calculation. Yeah. Just like I mentioned. Yeah. Anyway. Okay. Anyhow, it is really unstable for the final one. Even though this one is stable through positive feedback, this one, I mean, this one or this one, okay, it has a right half plane power. It is unstable. However, put it back to the original circuit, it will become stable. So you can see, unstable amplifier, but to get stable closed loop application. Yeah. And then if you are scared by unstable op-amp, it's everything I learned from microelectronics till now, the amplifier needs to be stable. Okay. Then you just change the size, right? For the amplifier itself, the output is connected, is fed back to the minus terminal, inverting terminal, to make this one stabilize. Congratulations, you make it. Piece of cake, right? Okay. However, this one, I promise you, it is stable for the overall amplifier. But if you put it back to the filter, okay, then sorry for that. The overall will become unstable. Okay, so this one is stable, but for the whole circuit, it's unstable. Are you happy? Of course not. That is the final result. We hope the final circuit is stable. We don't care the stability of the amplifier. Okay? That is one case. So a brief conclusion. You can see, for that case, with stable amplifier, the filter become unstable. With unstable amplifier, the stable becomes stable. So it means what? The stability of the final application is not determined by the stability of the amplifier. Okay? They can be irrelevant. I don't say they are irrelevant. No, I say they can be irrelevant. Sometimes they are relevant. They related to each other. Sometimes they don't. Okay? If you are not happy, you say, hey, that is some kind of circuit out of date, used in 50 years ago. Okay, allow me to show you. Even for this one. Okay, let's go to the bottom. If you look at this one, a very simple, what do we call it? Non-inverting amplifier, right? You learn it already from your microelectronics. I guess that is the first or the second application for op-amp. You learned from microelectronics. Let's go to the bottom to see all the details. You can see from the very beginning, you design some stable or unstable. Okay, let's go. For stable op-amp, you learned it already. So right now, I would like to show you, even though from the very beginning, you design an unstable op-amp. Unstable means what? Again, for our dominating power approximation, you set this one to be 0, then, and it is positive. Wow. Oh, dangerous, right? The power belongs to the right half plane. I mean, for S plane. Laplace, according to Laplace transform, you learn it from fundamental circuit theory. Okay, this is what you never touched before. You are afraid of that because all your teachers, all the textbooks told you, don't go over there. The earth is flat. Don't sail your boat to the end of the world. Otherwise, you will fall down to the hell. Okay? Columbus didn't buy it. So he sailed the boat to make a big turn back to his country. He became the most famous guy to explore our earth. Okay? Anyway, in the past, nobody would like to design anything like this. You always design for the single pole to be negative to the left half plane. But right now, I would like to show you. Even though you design something like this, the op-amp itself is unstable. Okay, let's go ahead. And how about the whole circuit? After some kind of very simple calculation, this is the final result. Very, very simple one. Okay? Yeah. Then, how about the stability of the overall non-inverting amplifier? Simply, you set this term to 0. So it means what? You have S equals minus P beta. Okay. Yeah. So anyway, this is minus, right? If this one is positive, congratulations. The final result, the power is still to the left. I mean for the overall circuit. Got it? Even the power for the op-amp is positive. It is no good. But the final power for the overall circuit is still negative. Only if this term is positive. Got it? So, this is what I would like to share with you, especially not this one. You can see, for open loop, I mean the op-amp itself, the power. This is the so-called S-plane after Laplace transform. Okay? In the past, humankind only focus on the left half plane here. And it means the power for your circuit, for your op-amp is negative. However, moments ago, after some kind of brief explanation, I told you, even though the power for the op-amp is positive, it is already to the right half plane, it will make the op-amp unstable. However, what is the requirement? For the overall circuit to be stable, only if its power is to the left. Okay, So the requirement is this, is that, blah, blah, blah. Okay. Yeah, anyway, something like that. That is some kind of, this is only special case, okay? And that is for the usual, for the general case. Anyway, anyhow, okay? It means what? According to such kind of derivation, only if the power of open loop circuit of the open loop amplifier is not larger than this boundary, you will help to make the overall feedback circuit stabilized. Don't cross the boundary. Okay? So what is the major difference now and the past? Okay, in the past, you guys only focus on this. Right? And after some slide, the explanation for the previous slides, not me, Professor Geiger encouraged to cross the boundary to the right, but not to right. Okay, to the right is right, but to right means wrong. Okay, you can cross the boundary for open loop op-amp. Okay, and then if you don't go too far, I mean another boundary, the overall closed loop op-amp, a closed loop amplifier will still be stabilized. Okay, so you can see for open loop, stabilized, unstabilized. But for closed loop, stabilized, unstabilized. And we say that we only care the stability of the final result. We only care this. Okay? So here is a new territory for all of you to enter. It means you can design an unstable op-amp, but in this region, the overall application will still be stabilized. In the past, we never touch it, but right now, you can try it. Okay, you need to thank Professor Geiger. Help us to find the piece of land missed in the past. Okay, be brave. Enter the boundary to here, but don't go too far. Another boundary, no. In this region, that is the new territory for all of you to explore. Okay, yeah. As I mentioned, don't believe our Earth look like that. It is not flat. Okay, don't be afraid to the boundary. You will fall all the way to the hell. No. Yeah. And this is some kind of equations for you. Okay, you can see from the equations we derive. Oh no, I didn't derive. I show you. You can see for open loop DC gain, it looks like that. Okay, so this power, it is positive. It is positive, but again, what is the mission for op-amp design? High enough gain, right? The DC gain should be high enough. So what is the requirement here? The right half plane power should be very close to the y-axis. It means the magnitude of this should be very small. The smaller of your positive power, the higher gain. That is the trick. Okay, in the past, actually, to achieve high gain, you are here. However, it is negative, right? And the magnitude is so small, the gain is really high. However, with low supply voltage, we cannot make it. Okay, so we can be brave, close the boundary to the right, but not far away from the y-axis. So right now, P becomes positive, However, the magnitude is still very small to make the overall open loop gain very, very high. That is the trick. Okay? And finally, we have closed loop gain. We don't care about this. We care about the stability. And yeah, for this term, you only need to make sure it is to the left. That's it, good enough. Okay, and since P is so small, so what is the final result? Yeah, so small, you neglect it, then, 1 over beta. Hey, look, from the very beginning, I show you. Okay, even here with P negative but very small in magnitude, you still get the same result, 1 over beta for the final result. So never mind, your op-amp is stable or unstable. Never mind, you how can I say? Yeah, anyway, it is stable or unstable. Never mind, the power is to the left or to the right. Only if they are very close to the y-axis, then I promise you, the final result is still the same, exactly the same, 1 over beta. Okay? And beta is determined by the feedback network, usually composed of resistors. We can match all of them to get very good, very stabilized beta. And it means the open loop DC gain can be stabilized. And also, look, it is to the left. It is very stable. Okay? And finally, allow me to show you some kind of settling performance. Yeah. If we have two kind of negative powers for the past and two positive powers currently, right? And this is some kind of analysis from Professor Geiger and his student. Now you can see there is some kind of transient response. Oh, if you connect this to be voltage buffer and then supply some kind of step function for the input. And how about the input? It needs to be followed or even have some kind of damping, right? Anyway, anyhow, yeah, that is the result. From the result, you can see P1. You have large negative power, very stable, but the scattering time is very long. And you can see you have small negative power. Yeah, the gain is higher than that. Okay, because if you have a look at the original one, the smaller the magnitude of the power, the larger gain you can achieve. So you can see, hey, P2 provide you larger DC gain and also smaller settling time. Bingo here, right? The settling time is here, right? And how about P3? Wow, even better. To the right, it is unstable for the op-amp itself, but the overall feedback circuit is stabilized. No worries. And then you can see, wow, it is not only stable output, higher gain, stable output, but also smaller settling time. Very good. This is for small positive pole, unstable pole for op-amp. And how about P4? Too large to the right. You can see. You say, hey, the settling time here? No, sorry for that. It is out of the boundary, right? And it doesn't come back. So the output will be wrong. Because that is the final result, what we expect. Never mind your op-amp is stable or not. I told you, you get the same result. But for P4, too much. Okay, the accuracy is out of the boundary. We have some kind of tolerance for accuracy. That is the final result. So positive, negative something. Epsilon means the tolerance. So it means what? Too right power will generate too much error after stabilization, after settling. Okay, so that is wrong. Okay, so anyhow, the final recommendation is don't always stay to the left plane. Be brave to the right, but not too much. Okay? Too much, you will cause, just like before, you will cause wrong result. I mean, too much error for the result. And also, if you go too far, the final result will become unstable. Don't cross the line. Okay? So you had a better design, your positive power very close to the 0. That's it. Yeah. Very, very good. So finally, do you need stable op-amp in theory? No. Do you need stable op-amp application? Yes. However, does a stable op-amp application require a stable op-amp? Hopefully, after my brainwashing, you know the result. No. Okay, that is me and Professor Geiger can help to brush all your brains. Okay, so after my class, all of you will have new brains. I mean, new viewpoints about analog IC design. That is what the most I can help. Okay, so we would like to present some kind of new approaches to design amplifiers. I mean, under low voltage situation. And Professor Geiger would like to provide some kind of preliminary experiment result for you to refer. Yeah, I met him in, right? So all the materials here, actually, they were prepared more than 15 years ago, right? If you are interested, what is the new approaches? Oh, just Google online, or you can have a look at Professor Geiger's main page, homepage, in Iowa State University issue. Okay, yeah. So let's go further. How can you make your op-amp become unstable? Positive feedback will be the king. Okay, so allow me to have some kind of very brief explanation. For example, this one. It is possible. Yeah. Okay, you can see. If you increase the V out, so from the viewpoint of AC operation, right? The higher AC output, it means what? The more AC current it flows. Got it? Got it? So how to reduce it? We hate it because we would like on the to the other side how to enhance RO. We hope, even though VO is varied, we hope IO is fixed. Okay, so my explanation is, for example, if it is increased, to make IO stabilized, fixed, then the current here needs to be reversed. Because if you forget about this, then the IO will be increased. So you need to reduce it here. And how? Okay, very simple idea. You can see? This is minus V out. Okay, so the V, if VR is increased, then here will be decreased and VGS will be decreased. Oh, no worries. No worries. The IO here will be decreased. And the overall IO is this original IO plus IO prime here. So if VR is increased, IO will be increased, but IO prime will be decreased. Congratulations. If you have a good design, they can cancel each other. Got it? However, this is only some kind of preliminary logic thinking. And how to make it, if you would like, you need to derive everything by yourself. Okay? Yeah, anyway. For Professor Geiger's work, they try to tune this one. Okay, that is really, because that is the first idea. Okay, so how much, yeah, as I mentioned, IO, the original one, and the extra one, you would like to compensate IO variation by IO primes variation. Okay, but how? You need to do some kind of fine tune. So I wouldn't like to show the final result for you. I only explain this. And then the other one is positive. Oh, this one is even better, even easier to understand. For some kind of positive feedback existing on us already, allow me to show you this one. See? It looks like current mirror, however, they have some kind of close interconnection. My gate connect to your Chen. Your gate connect to my Chen. Please keep this in mind. A very important building block to provide you negative impedance. Got it? Negative impedance. And that is what I mentioned. Where? Anyway. Positive feedback, okay? Something like that. Anyway. What is the idea? Oh, for this one, if Q3 and Q4 are the same, then after some kind of small signal derivation, the equivalent impedance becomes -2 by GM. Okay? GM is the transconductance for G3 or G4. That's it. I think the students of Professor Zhang, Shengliang Zhang, okay, they apply such kind of small circuit very much for RF circuit. If you go back to look the RF chip, they apply such kind of negative impedance circuit block very, very much. Okay. Anyway, anyhow, what is the fundamental idea? Very easy, very simple. Because except for such kind of negative impedance circuit, for all the others, their impedance are positive, right? So we try to compensate for all the other positive impedance by this negative one. That's it. That is the idea. Okay? So the conductance you have, everybody have positive GO, right? And myself have negative GO. So I would like to cancel each other. No output conductance. It means no extra AC current. The GO becomes 0, right? And RO will become infinite. Congratulations. Anyway, anyhow, after some kind of brief intro derivation, you get this. Yes. What is the problem? You can see the transconductance of Q4 or Q3 as you like. Would like to compensate for all the others, all the other positive terms. However, only GM, they can cancel each other. Never mention about GO. GM cannot be used to match GO. Got it? Got it? That's it. Sorry for that. So even during design, oh, you make perfect one. Oh, congratulations. For your post simulation under TT, under blah, 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 oh, they cancel each other. So what is the gain? What is DC gain? You make this one to 0, and that one is also 0, right? It will become infinite. However, it never be true after fabrication. Sorry for that, because it is no way for you to match GM to GO. All right, that's it. Okay, another one. Yeah. Anyway, it's impossible. Okay. And the other one is this and that. That is the trick Professor Geiger and his student played. So they try. What is the modification from the original one? Original one, it is diode connected, right? So before fabrication, Professor Geiger and his student change it. See? Some kind of bias. And then they fine-tune the bias of chip after fabrication. That's it. Got it? All right. And we can all of this. Again, this is no way to match. No worries. They have some kind of fine-tune. So let's go for the implementation, forget about the detail, because I don't recommend you to follow this because it needs some kind of fine tune. Okay, after fabrication, it doesn't make any sense. Anyway, anyhow, allow me to show you the result. They use for concept proof. Okay, to prove the concept, actually they didn't use low supply voltage, but they would like to show you how good the result will be. Okay, with some kind of fine tune. Okay, that is the process AMI in Austria, I guess, in Europe. Maybe that is the final one. With a very old process, blah, blah, blah. Okay, that is the diphoton, and that is the measurement. You say that is the input, and that is the output. You need to pay attention. The input and output with different scales. Okay, anyway, anyhow, it only means that with very small input and after amplification, only one open. Wow, you have very good square wave output. All right, and the control voltage, as I mentioned, that is for fine tune. Anyway, anyhow, okay, that is the final result. They fine tune the control voltage and to measure the DC gain. You can see, wow, for only one stage, it can achieve the most is 80 dB in gain. 80 dB means what? 10,000. Wow, my gosh. Really, really terrible. Okay. Not terrible, really amazing. All right, however, what is the problem? You need to fine tune this, right? So Professor Geiger would like to sense whether or not the control voltage is stable according to the other variation. Oh, okay, later, okay. And this is some kind of output swing, okay, versus the gain. You can see the tendency look like that. The higher gain, okay, means the smaller peak-to-peak output swing. If you lower down the gain, then the output swing will become larger. Okay, so if you look at this, around 60 dB, it means 1,000 in gain, right? And the peak-to-peak output swing is almost 1 volt, good enough. And then, how about the stability according to temperature? You can see the measurement of at 0 degrees and 23 degrees. Look, the peaking areas are about the same. So what is the meaning? It means that is some kind of preliminary result, right? So you can see here, if you wouldn't like to fine-tune the result, then during your design, you can fix your V control in this region, in the middle of this region. And at least they can provide you the highest again is more than 75. It's still very close to 10K. Okay? So would they like to go back to redesign the V control? They wouldn't like to have fine-tune? No. They go further. They, after such kind of very good result, they cooperated with TI for ADC design. Okay? Yeah, some kind of performance summary. Very good, very good. Okay, so they would like to have this one, even better one. Okay, that is almost the final skill, trick I would like to teach you for this chapter. Positive feedback telescopic cascode. Okay? What is telescopic? Oh, wow. Okay, that is original one. For this level, that level, they apply the same bias for the same level, right? That is for telescopic. However, to make it become positive feedback, pay attention to such kind of cross connection. Got it? Cross connection is really important. Just what I show you, right? Your gate to my drain, my gate to your drain, you have cross connection. Yeah. So that is a very important idea for you, for such kind of connection. Instead of that, parallel connection. No, for this one, Congratulations. Negative impedance to provide positive feedback, blah, blah, blah. Okay? Anyway, anyhow, after some kind of calculation, they will show you, whoa, the gain is such high. If you are not happy, you can, because this is only single stage, right? You can provide the second stage. Wow. And one order higher for gain. All right? So therefore, they would like to prove it. Okay. They don't prove this. They go back to for this one. They have two versions. One is this. Original telescopic case code. No positive feedback. No cross connection. For the first chip, right? And for the second chip, they would like to tell the difference to see how good, how right, or how wrong it will go. Okay, that's it. Allow me to show you. For the two chips, that is the difference. Wow. With the same size, with the same power consumption, you can see, wow, it is increased by almost 20 dB. Okay? That is the power of positive feedback. And how about the phase margin? Almost the same. Only a little bit difference here. For there and there, the same. So they have almost exactly the same phase margin. All right? And that is the conclusion. See? What is the major difference? The gain. And how about the others? Almost the same. The same supply voltage, the same current, it means the same power consumption, the same phase margin, blah, blah, blah. All of them are the same. Are almost the same. The only difference is what? The gain. You pay nothing to get something. That is really interesting, really amazing. Okay? They are not bluffing. They do it, they prove it through real chips. Okay, so that is some kind of to cooperate with TI, but they only, TI has some kind of commercial ADC chips. Okay, they only help TI to replace the original op-amp, original telescopic blah blah op-amp with their new design. That's it. And then go for fabrication. I got the chip photo. I couldn't see any detail inside. So I wrote email to Professor Geiger to ask for the correct one. However, Professor Geiger told me that is some kind of commercial secret. Okay, so under the regulation, under the requirement of TI, they cannot show anything. So they have such kind of nothing to show micro photo, but they have the amplifier, blah, 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 blah. Okay, anyway, anyhow. Allow me to tell you more. Actually, they dug out, they removed the original amplifier and put their own inside. What is the result? It's really interesting. They only occupy 1/3 of the area for amplifiers. Okay? And then after fabrication, they have some kind of blind test. They have two chips. One with new op-amp design, with positive feedback. The other one is original one, so they have some kind of sticker to cover both. And send all those back to TI's lab for measurement. And after measurement, they provide some DNL, I know that is the most important for ADC, right? And after that, they asked the TI engineers to check which one is the new. They thought, they selected the wrong one because they have two chips, right? The performance is about the same, but Yeah, one is a little bit better, the other one is a little bit worse. So the engineer select the a little bit worse chip. But after they get rid of the stickers, sorry, the one with a little bit worse performance actually is the original chip. And the a little bit better one actually is the new one. Wow! As I mentioned, they dug out the original amplifier to replace with the new one and occupy only 1/3 of the area, but they provide about the same. However, the engineer tell the difference a little bit better actually is for the new one instead of the better one. So TI was amazed. So what is the consequence? Oh, they get help from the layout engineer, right? To redo the layout because all those are empty, right? So they reduce the layout for fabrication, and after fabrication, after packaging, usually the chip will say, oh, 2020, maybe 36. What is that? That is the year of the fabrication, I mean after packaging, and that is the number of weeks. For each year, we have 50-something weeks, right? Yeah, so Professor Geiger told me, after some day, with new op-amp, and before that, old op-amp, and the new one actually, the chip size is smaller than before, okay? But TI still sold the chips with exactly the same price. TI made much more money, much more profit than before. They are really, really happy. Before that or after that, actually, Professor Geiger and his student get a lot of help from TI for chip fabrication and also project sponsored by TI, blah, blah, blah. Okay, that is really amazing. What is amazing? If you stick to the original thinking, for your open loop, open, you always stay to the left. Left is wrong. Please go through the boundary to the right, but not to right. Okay, if you go even further to go through another boundary, sorry, the closed loop operation will become unstable. So here is the new territory for you. They not only say did, they did to prove their concept is totally correct. And hopefully all of you, because if you study the same class in NTU or all the other, oh sorry, my secretary is calling me. Okay, anyway, anyhow, please open your eyes, okay? Close the boundary, not far, not too far away. You will have much better result and also life for your own future. That is the end of the open. For all the others, just read it by yourself. How about the others? You can see, double closing. Okay, more negative feedback, more negative impedance, more positive feedback. It means higher gain, blah blah blah. But the price is what? It is even harder to design. Even though you have only one close connection, it's really hard to stabilize it. My student told me. Okay, but if you made it, if you make it, you will enjoy the fruit. Yeah, with the same or even smaller chip area, you can provide better performance, higher gain, I mean. Okay, and how to do the rail-to-rail amplifier design? That is the final one. Okay, piece of cake. Because for NMOS, it doesn't work here, and for PMOS, it doesn't work there. So you connect them in parallel. In parallel, please, not in series, in parallel. Then you can work from the top to the bottom. That's it. However, in the middle, both of them are functional, right? So for the GM, it will look like that. Okay, this is for PMOS, that is for NMOS, and in between PMOS and NMOS pair, both functional. Or if you hate it, actually, is it bad? Not so bad, because only if the gain is good enough. We don't care about the linearity of the open loop one. We only focus on the closed loop one. However, if you are interested, you can make it flatten, right? So, yeah, the final term for you, constant GM. Constant GM, rail-to-rail open design. You can Google online or search through IEEE Explore. That is the end of the whole open design. Yeah. Finally, what is my hope? After my teaching, I hope you guys will become better analog IC designers than all the students in the other university. Okay,